Two perfectly accurate clocks glow on the dashboard as your spacecraft points straight toward a black hole. One clock stays linked to a probe far away where gravity is weaker. The other travels with you. At first, they match perfectly. Then the black hole starts filling the window. Your clock falls behind. You don't feel anything strange. Your heartbeat stays normal. Your thoughts move at the same speed. Every second inside the cockpit still feels exactly like 1 second, yet the clock far away is racing ahead. And the closer you get, the bigger the difference becomes. To someone watching from a safe distance, your spacecraft seems to slow down near the event horizon. The light leaving your ship stretches toward red, grows weaker, and takes longer to arrive. That observer may never receive an image of you actually crossing the edge, but inside the ship, you could cross it after only a limited amount of time. So which view is real? The one from far away or the one inside the spacecraft? The answer is both. We're going to hover just 1% above the event horizon, where the difference between the two clocks becomes extreme. Then we'll test it with a radio signal and watch the numbers climb to a result that shouldn't seem possible. After that, the pilot will shut down the engines. And the moment the ship stops fighting the black hole, the entire meaning of time begins to change. The trip begins far enough from the black hole that both clocks still match. One is inside the spacecraft with you. The other is connected to a probe waiting much farther out, where the black hole's gravity is weaker. Second after second, they stay together. For now. Ahead of the ship, the black hole looks like a dark circle surrounded by glowing, twisted light. That darkness isn't a solid object. It's a shadow created by light that can't reach us from certain directions. At the edge of that shadow is the event horizon, the point where nothing can send a message back to the outside universe. For a black hole that isn't spinning, scientists describe the size of that boundary using something called the Schwarzschild radius. Our target is terrifyingly close. The spacecraft is going to stop at 1.01 Schwarzschild radii. That's only 1% above the event horizon. The engines fire. To keep the ship from falling, they blast exhaust toward the black hole, creating thrust in the opposite direction. The closer we get, the harder they have to work. A warning appears on the main display. Hovering force increasing. In real life, the crew wouldn't survive this. The acceleration needed to hover so close to the horizon would crush them. For this experiment, we'll assume the ship has some kind of advanced protection system that keeps everyone inside safe. The technology is imaginary. What happens to space, light, and time is based on real physics. At first, the view changes slowly. Then the stars begin to bend. Light from behind the black hole curves around it and enters the cockpit from directions that should be impossible. Stars that should be hidden appear stretched into bright arcs around the darkness. The black hole no longer looks like a simple dark ball. Its shadow grows across the window. Glowing rings twist around it. The sky itself seems to fold, and the deeper we go, the stranger it becomes. The outside universe starts getting squeezed into a smaller part of the sky behind us. More of the cockpit view turns black, while the remaining stars crowd together inside a warped patch of light. Then the navigation system marks the photon sphere. This is a region where light can travel around the black hole in unstable circles. A beam of light on exactly the right path could loop around it. But the smallest change would send that light either back into space or down toward the event horizon. The spacecraft passes below the photon sphere. We still haven't crossed the horizon, but visually, it almost feels like we're already inside. Darkness fills most of the window. The universe behind us now looks like a shrinking, distorted opening. And there's a problem. The crew can't actually see the event horizon. There's no bright line floating in space, no wall, no glowing surface. Nothing outside tells us exactly where the point of no return begins. The ship has to calculate it. Using the black hole's mass and our distance from its center, the computer projects a thin marker across the cockpit glass. That line isn't really out there. It's only showing us where the math says the horizon should be. The engines push harder. The whole ship begins to vibrate. Then the display changes. Distance, 1.01 Schwarzschild radii. We've reached the target. The spacecraft is now hovering only 1% above the event horizon. This is where the clocks are about to disagree, in a way no normal clock on Earth ever could. Before we started the descent, we left a second probe much farther out. It's hovering at 3 Schwarzschild radii from the black hole's center. The probe carries a radio transmitter. According to its own clock, it sends a signal at exactly 10 megahertz. That means it produces 10 million radio wave cycles every second. Inside the cockpit, the crew turns on the receiver. If time is passing at the same rate in both locations, the signal should arrive at 10 megahertz. The transmitter activates. Static fills the speakers. The receiver begins searching. The display reaches 10. Then it keeps going. 12, 20, 37. The crew checks the system. No error. The probe hasn't changed the signal. The number continues climbing. 53, 68, 79. Then the display stops. 82 megahertz. The same probe that's sending a 10 megahertz signal is being measured here at about 82 megahertz. That sounds impossible. It isn't. The signal has experienced gravitational blue shift. That simply means the radio waves are measured at a higher frequency after traveling deeper into the black hole's gravity. The transmitter is still producing 10 million cycles during each second on the probe. But the clock inside our spacecraft is passing much more slowly compared with the probe's clock. During roughly 1 second here, a little more than 8 seconds pass where the probe is hovering. So our receiver counts more than 8 times as many radio wave cycles during one of our seconds. That's why 10 megahertz becomes roughly 82. The clock beside you is falling far behind, and yet you don't feel it. Your heartbeat sounds normal. Your hands move normally. The crew speaks at a normal speed. The clock on the dashboard ticks once per second, just like it always has. You never feel your own time slowing down. The difference only becomes clear when you compare your clock with one somewhere else. So how can 2 perfect clocks show different amounts of time? The answer starts with a simple idea from Einstein. Picture yourself inside a sealed room floating in empty space. Now the room starts accelerating upward. A beam of light enters through one wall and travels toward the other side. While the light is crossing the room moves upward. From inside, the beam seems to bend downward. Now place that same room in a gravitational field. Light bends in a similar way. This idea is called the equivalence principle. It tells us there's a deep connection between gravity and acceleration. And that connection changes how space and time behave. Light always moves at the same speed for someone measuring it nearby. It doesn't simply slow down like a car entering heavy traffic. So if gravity bends the path of light, then space and time have to change together. That's the key. A black hole's mass bends space-time, and a clock closer to the black hole experiences less time than a clock farther away. The black hole isn't damaging the clock. It isn't making the gears stick or draining the battery. The clock is working perfectly. It's simply located in a place where time passes differently compared with the region above it. But there's one detail that changes the entire experiment. Right now, we're hovering. The engines are fighting the black hole every second. They're forcing the ship to stay in place instead of following its natural path downward. Falling will be completely different. The pilot looks at the shutdown control. Outside, the black hole covers nearly the entire window. The distant universe has been squeezed into a bright, twisted patch behind us. The engine warning turns red. The probe's clock moves farther ahead. The pilot starts the countdown. 3. The engines reach maximum power. 2. The horizon marker moves across the glass. 1. The pilot shuts down the engines. The roar disappears. So does the force pinning the crew into their seats. For the first time, the spacecraft isn't fighting the black hole. It's falling freely, following the natural curve of space-time. Inside the cabin, everything suddenly feels calm. A loose pen floats above the control panel. The crew can move without struggling against the ship's brutal acceleration. The dashboard clock keeps ticking at its normal pace. Nothing feels slowed down, nothing feels frozen. Yet far away, the probe sees a completely different version of what's happening. As the spacecraft falls closer to the event horizon, every radio signal it sends takes longer to arrive. The light leaving the ship has to climb away from the black hole's powerful gravity. As it does, the light stretches toward red and loses energy. Scientists call this gravitational redshift. In simple terms, the ship's light becomes redder, dimmer, and harder to detect as it tries to escape. To the distant observer, the spacecraft seems to move more slowly with every passing moment. Its radio messages become drawn out, its image fades. Eventually, the ship appears almost frozen near the event horizon. But there's an important detail. The observer doesn't keep seeing a bright, clear picture of the spacecraft forever. The signals become so weak, delayed, and redshifted that they eventually disappear into the darkness. From far away, the final moment of crossing is never seen. Inside the spacecraft, however, the journey continues. The event horizon marker moves closer across the window. The crew watches the numbers fall. Then the marker passes over the cockpit. Nothing happens. There's no explosion, no flash of light, no solid wall. The crew has crossed the event horizon, and they may not even realize the exact second it happened. For them, the crossing took a limited amount of time. For the distant observer, no final image ever arrived showing it. This is where the two viewpoints seem to completely disagree. But neither one is wrong. There isn't one master clock ticking at the same speed everywhere in the universe. Time depends on where you are and how you're moving through space-time. Now, the spacecraft is inside the point of no return. Outside the event horizon, there are still paths that can lead away from the black hole. Inside it, every possible path takes you deeper. Even light can't escape. That doesn't mean light suddenly slows down. Anyone measuring it nearby would still see it moving at the speed of light. The problem is that space-time is bent so strongly that every direction leading into the future now points farther inward. You can aim a flashlight away from the center. The beam will still move forward, but forward no longer leads back to the outside universe. And that raises a strange question. If nothing can escape, could you lower something across the event horizon and pull it back? Imagine the ship is still outside, holding one end of an extremely long pole while the other end reaches toward the black hole. At first, it seems like a loophole. The lower end could cross the horizon, and the crew could simply pull it back. But real objects don't work that way. No material is perfectly rigid. When you pull one end of an object, the other end doesn't react instantly. That movement has to travel through the material, atom by atom, and it can't travel faster than light. Near the event horizon, the lower part of the pole would need much more force to stay in place than the upper part. The stress would become enormous. The pole would stretch, heat up, bend, or break. And once part of it crossed the horizon, no message from that section could travel back out. The pole couldn't be used to reach inside and retrieve something. If the crew released it, the pole could fall freely, just like the spacecraft. But another danger would soon take over: tidal forces. Gravity is stronger on the side of an object that's closer to the black hole. If your feet were falling first, they would be pulled more strongly than your head. That difference would stretch your body from top to bottom while squeezing it from the sides. This is called spaghettification. And yes, it's a strange name for a deadly process. Near a smaller, stellar mass black hole, these forces can become extreme before you even cross the event horizon. A person or spacecraft could be torn apart early in the fall. A supermassive black hole is different. Its event horizon can be millions of miles wide. Because it's so large, the change in gravity between your head and feet may be much smaller at the edge. You might cross the event horizon without feeling anything unusual. The danger would come later, deeper inside, as the tidal forces grow stronger. So the event horizon itself isn't what destroys you. It's simply the point after which escape is no longer possible. The clock inside the ship keeps ticking. Far above, the probe's clock moves farther ahead. The two clocks are still accurate. They're just experiencing different amounts of time. And now we can answer the main question. Why does time slow down near a black hole? The black hole doesn't damage the clock. It doesn't make the hands stick or cause the battery to weaken. Its gravity changes the shape of space and time. A clock closer to the black hole experiences less time than a clock farther away. The person carrying that clock never feels slowed down. The effect only appears when the clocks are compared. To the distant observer, the falling ship seems to slow, turn red, and fade. To the crew, time moves normally, and the event horizon is crossed after a limited number of seconds. Neither observer has the only correct version of what's happening. Two people can move through the same universe and experience completely different amounts of time. Near a black hole, time isn't broken. It's doing exactly what space-time tells it to do, and that leads to an even bigger mystery. What kind of object could collapse with enough force to bend space-time so deeply that a black hole is created in the first place?